Okay, so we are going to talk now about, we talked in chapter 7. Chapter 7 is differential equations. And we talked in section 7.1 about, well, that was an introduction to differential equations to get you familiar with what differential equations are. And then in section 7.2, you learned about direction fields. So in other words, if you have a differential equation, based on the differential equation, you're able to draw a direction field, and direction fields allow you to see what typical solutions are going to look like, depending on different initial conditions. And even though we might not be able to solve a differential equation explicitly, with a direction field, we can at least qualitatively see what solutions to the differential equation would look like, what families of solutions would look like in the direction field. And then also we learned about Euler's method, which was a way to find if we wanted to approximate a solution to a differential equation at a certain value of x or a certain value of t, we could do that using Euler's method. And the more step sizes we used in Euler's method, the better the approximation would be. Now, in section 7.3, what we're doing is we are actually going to solve some differential equations. And a very well-known differential equation, differential equations that can be solved, or usually you can find an explicit solution, would be if the differential equation is what's called separable. Separable. So below here, what you have is you have an initial value problem, okay, because you're presented with a differential equation here, and then you're also given an initial condition. The solution to this differential equation requires that when x equals 0, y equals 2. So there is a unique solution to this differential equation. There will be a unique solution. And just a note here, how can we write y prime on the left side? How can we write y prime?
2y.
This will be helpful. That's right, dy dx. Good, Jacob. Good, Maria. And for separable differential equations, it's good to use the Leibniz notation here. Okay, dy dx is Leibniz notation for the derivative of y with respect to x. Okay, so let me go ahead and show you what it means to solve a differential equation by separating the variables. On that note, I'll go to the next page and we'll look at the solution. So we want to separate the variables. Let's separate the variables. Okay, so again, y prime is x squared over y squared, but that means that dy dx is x squared over y squared. Right? So the dy dx is, as you know, it's a derivative or a rate. But a rate can be thought of as, well, like in Calculus 1, how many of you saw that dy dx can be approximated by the ratio of these two differentials, delta y over delta x? How many of you saw it? Okay, Nathan remembers that, and Sean, and a number of you. So the point is that dy dx this is a rate, but a rate is also a fraction because of this relationship here. Okay, so a rate really can be thought of as a fraction. And so what I can do is I can try to get the x variables on one side of the equation and the y variables on the other side of the equation. That's called separating the variables. So what I do here in this next step is I multiply the differential equation by y squared on both sides. And so what happens is, on the left side here, the y squared simplify out, and you're left with y squared dy dx, okay, equals x squared, right? Y squared times dy dx equals x squared, all right? And then what we can do is we can, well, let me just clear it here. We can, at this stage here, we can multiply both sides of the differential equation by delta x, effectively. And then on the left side, I mean, it's really a differential, essentially, but let the differential get smaller and smaller. You end up with y squared dy equals x squared dx. So are we good up to this part here before I continue? Okay, Jacob's good. Wonderful. And okay, Tal's good. Excellent. Samuel's good. Wonderful, wonderful. Well, so we do have an equation here. We have an equation. And in this equation here, if we integrate the left side of the equation, what do we have to do the right side of the equation?
Integrate.
That's right. If we integrate, that's right, Maria. If we integrate the left side, that's right, Renat. If we integrate the left side of the equation, we have to integrate the right side of the equation. And so we do that. We do that right here at this step. But of course, these are indefinite integrals. And so when you integrate y squared dy, you get y cubed over 3 plus constant of integration on the left. And then on the right side, so you know, on the left, you're integrating with respect to y. The integral of y squared with respect to y is y cubed over 3 plus constant of integration c1. And then on the right side, the antiderivative of x squared is x cubed over 3 plus c2, which is a different constant of integration. Well, the c1 and the c2 could have the same values, but they don't have to have the same values. Okay, so they're just constants of integration. But what I'm going to do is I'm going to subtract c1 from both sides of this equation now. And I arrive here at this last step where y cubed over 3 equals x cubed over 3 plus c2 minus c1. And I'm going to call c2 minus c1, I'm going to call that c3. That's my, so I don't want to carry around two different constants of integration. So I'm going to call it c3. c2 minus c1 is c3. Please let me know if you have any questions. Okay, Nathan's good. Excellent. Okay. Are we ready to move to the next page? Okay, Maria's good. Leping's good. Baraka's good. Tall's good. Okay. Well, we still now have to solve for y, right? We need to find out what is the solution to this initial value problem. What does y equal? So obviously, or it should hopefully be obvious, that I have to take this equation and solve it. I have to solve this equation for y. And so what I'm going to do is I'm going to multiply both sides of the equation by 3. So I'll get y cubed. And of course, on the right side, the 3 gets distributed to both of those terms, giving me x cubed plus 3c. And now, at this stage, I'm going to call 3 times c3. I'm going to call that my constant k. So when I get to the, like now I know that basically I'm going to solve for y, and I'm not going to need to do any more manipulations on my constant of integration. So I'll just call it big constant k. To that end, then, y cubed equals x cubed plus my constant of integration k. And now I'm gonna take the cube root of both sides. So what I'm doing here at this stage here is I'm raising both sides to the 1/3 power, so I can isolate the y. Y third raised to the 1/3 power, you multiply the exponents. 3 times a third is equal to y. And so I end up with a family of solutions. But now, remember, we were told that y of 0 was equal to 2, right? So if that's my initial condition, I can solve for this constant k of integration. I can solve for it. And when I do that, when x equals 0, y equals 2, I substitute that in my solution and solve for k. And it turns out that k will equal 8. Leping, question? Are there any questions?
Yeah, Professor, why not show the C3?
Well, I have here 3 times C3. It's easier for me to call that just some constant K. I find it easier. But you could keep the 3 times C3 there and, carry it around if you wanted. And that would be okay.
No, I mean not 3 times C3, just so C3. Why not we can show C3?
You mean on the step above?
Yeah.
Well, what I'm doing is I want to get the y cubed by itself. because I want to, like, so like on this step here, why am I multiplying through by 3 on both sides of the equation? It's because I want to get y cubed alone so I can solve for y. So by multiplying through by 3, 3 times y cubed over 3 just gives me y cubed. But then I got to multiply the right side of the equation by 3. And so when I distribute the 3, I'm going to get, you know, an x cubed term. But then I'm also going to get a 3 times 3c3 term. Well, 3 times a constant is just some constant. So I call that constant k. See that? All right, Leping, is that okay?
Yeah, I understand the whole process, but I just don't understand. You want to get the solution for constants, right? But
Correct.
from the top equation, you can get the constants for C3. So plus x equal 0, y equal 2, you can get a constant for C3, but it's different number. It's not equal 8.
Right. What Leping's saying, it's a good point. At this stage, I mean, I could solve for the generally I like to solve for and get like y. I like to get my explicit solution before solving for the constant. But you don't have to. You could indeed put in, you know, the 2 here for y and the 0 here for x, and solve for that constant like ahead of time. So like here, I can solve for the constant by substituting in the initial condition right there. And that would give me 8/3 equals C3. So then I could you know replace C3 with 8/3 and then continue. So yeah, you can do that ahead of time. You can solve for the constant ahead of time. Very good point, Leping. And some students like to do that. I think Leping's one of them. And that's fine. Okay, all right. Well then, excellent. If are there any other questions before I go to the next page? Okay, well let me go to the next page then. So the solution to the initial value problem is y equals the cube root of x cubed plus 8. Okay, IVP stands for initial value problem. Initial value problem. Abbreviation. And what I have below here is I have just I mean this example that we are talking about from section 7.3. Let me see here. It is, I just gotta find it here. Hold on, this page. It's example 1 that we're looking at. And this is figure 1 from section 6.3. And this figure, I just wanted to give you a little perspective. It shows graphs of several members in the family of solutions of the differential equation in our example, which is example 1. The solution of the initial value problem that we did is in red, and I'll highlight that for you right now. So here's the point. Here's the point 0, 2 that our solution passes through. And so it's going to be this solution here. Kind of best I can do it there. Passes through the coordinate 0, 2. Okay. Are there any questions on that? Okay, may I go to the next example? I think the next example I'm going to, Ria's good, excellent. I think I'm going to go in the ebook and bring one up here. So one moment. I'll just mention this. It says that MindTap, which goes with the ebook, is scheduled to have maintenance performed on Thursday, July 8th from 5 to 6 a.m. Eastern Time. During this time, MindTap will not be available. We apologize for any inconvenience. So that means this Thursday from 5 a.m. to 6 a.m., the ebook will not be available. Okay, let me make a note of that. A reason it, I mean, well, it's good to know, but also, you know, if you're taking, like, doing the remedial problems at that time, the ebook won't be available for an hour. So if you're scheduled to take your remedial problems this Thursday from any during the time of 5 to 6 a.m., I recommend you change your time. This just came up. I didn't know about this. Hold on here. Let me just snap a photo of that. Okay, good. All right, now let me go into the ebook here. Okay, I want to bring up an example here. Okay, let me go into the ebook. Hold on. Okay, so they talk about in section 7.3, they have examples, and one they talk about a separable equation with an implicit solution. Okay, so I just wanted to make you aware that, I mean, really what to me is very valuable is finding an explicit solution. But because then you have a formula for your solution, you know, y equals something. But you see here in example 2, they separate like in the in this here, they separate the variables. They have the y variables on one side, the x variables on the other, and then they integrate both sides. And then they get y squared plus sine y equals 2x cubed plus a constant. And that's called an implicit solution. You're not solving for, you're not like getting an explicit solution for y. You can't solve that for like and get y equals a function of x. So this is called an implicit solution. I just want to make you aware of that, because, you know, it's just something you should be aware of. Are there any questions on that? Okay, well then let's move on. Let's move on here. The book has some good examples. Okay. They talk like in example 4. They do an example where they find the current in a circuit by solving a separable equation. Okay. So how many have seen? Now this is not a formal physics class, but what differential equation is this here? Has anybody seen this? Let me highlight it here. This differential equation maybe in a physics or engineering class? Sean has. Okay. And what's the name of this differential equation? Does anybody know? Begins with a K. How many have heard? That's right. Good, Sean. Kirchhoff's law. Good, good. So yes, this differential equation is a differential equation that like if you have a circuit that has a resistor and an inductor and would have a capacitor, a resistor, and would need a battery source, a voltage source. And you'll learn about this as you move on in math. But that's called Kirchhoff's law, or some people call it Kirchhoff's law, and it's a differential equation. Okay, and the differential equation, again, it's a differential equation that can model the voltage and current I want to say this right, capacitance in a simple circuit. Okay, so there's an example of where you have a differential equation, and they go through and solve a differential equation. But maybe we'll come back to this. But let me move forward here. I want to get to a few more things here. Okay, so something I want to talk about here is orthogonal trajectories. Okay, so an orthogonal trajectory, and I'll highlight this. Hold on here, class. An orthogonal trajectory is a family of curves, is a curve that intersects each curve of the family orthogonally or at right angles. This is going to be very important in multivariable calculus, okay, which incidentally I teach in the fall. So you see the picture there in figure 7. You have a red curve, and it's intersecting this family of curves at right angles. Okay, so the family of curves in figure 7, well, I want to say this the right way. The red curve is an orthogonal trajectory to that family of curves. Okay, and let's see here. We go down a little bit here. Here's an example also of orthogonal families of curves. The circles, the line segments intersect the circles at right angles. At every intersection, you have a right angle. So these two families of curves, circles centered at the origin in figure 8, and the lines through the origin are orthogonal families. Okay, so it's important, this concept. So let's look at example 5. Well, are there any questions so far? Okay, then let's look at example 5 here. Okay. So they want you to find the orthogonal trajectory of a family of curves where x equals k times y squared, find orthogonal trajectories of the family of curves, which is x equals k times y squared, where k is an arbitrary constant. Okay, so x equals k times y squared, okay, that's a family of what? X equals k times y squared would be a family of what types of, that's right, Renaud, parabolas. That's right. Okay, and in fact, are the parabolas up and down parabolas or sideways parabolas? Sideways, that's right, Renaud. That's right. So we want to find the orthogonal trajectories to that family of curves. So what we're going to do is, well, we need to get a differential equation involved here, right? So we're going to take x equals ky squared. We're going to take that equation and we're going to differentiate it. Okay, we're going to differentiate it. So what type of differentiation is being done here? You start off with x equals k times y squared, and then, well, actually, hold on, let me go to the whiteboard. One moment. Let me do it. Here's x equals k times y squared, and you're going to differentiate both sides of this equation with respect to x. And you end up getting, you get 1 equals, hold on here, you get 1 equals 2k. Well, actually, hold on. I want to do one thing. Let me do one thing here, class. Hold on. On the right side. Okay, so that constant k can be brought out in front. And so you have out in front of the derivative. And so you have d dx of the y squared. So 1 equals k times, all right, now what you get is 2 times y times dy dx. Okay, so what did I just do here? What kind of differentiation is this that we just did here? When I take the derivative of y squared, I get 2 times y times dy dx. What type of differentiation is that? Do you remember? Begins with an I.
Chain rule.
Well, it is the chain rule, but it's also, as Jacob says, it's implicit differentiation. But implicit differentiation is based off of really the chain rule, because we know differentiation. We know that y implicitly is a function of x. So if we take the derivative of y squared with respect to x, well, the outer function is y squared. That's how we get 2y. And then the derivative of y with respect to x is dy dx. So we need to know this in order to do this problem. Are there any questions? Okay, then let's get back to the book. So, okay, 1 equals, then for this example 5 that we're looking at from section 7.3, dy dx then would equal 1 over 2 times k times y. And they state here, they state that the differential equation depends on k, but we need an equation that's valid for all values of k simultaneously. So to eliminate k, okay, because remember we're trying to get equations for this family of orthogonal trajectories. So what they do is they say, well, okay, if x equals k times y squared, then k equals x over y squared, right? Because we were told that x equals k times y squared. And so now what we're able to do is we're able to substitute in for k, we're able to substitute in the x over y squared. And this is going to then give us, then dy dx equals y divided by 2x, right? That's what we're going to get. Are there any questions on that so far? Okay. Well, what do you think we're going to do with this differential equation here? First of all, is the differential equation separable? Can we separate the variables? I guess that's really the key question, right? We absolutely can. That's right, Sean. We can separate the variables. And when we separate the variables, okay, well, we can separate the variables, but hold on. Before we do that, something I forgot to mention. We're not there yet. For this set of parabolas, okay, the set of parabolas x equals k times y squared, the derivative with respect to x for those parabolas is equal to y divided by 2x. Okay, but we are interested in the family of orthogonal trajectories to those parabolas. And well, how would we find that? Well, if you have I mean, let's think of it like this. Let me go back here. Hold on. Let me go back to the whiteboard. Hold on here. Hold on. Where's my Let's do something very simple here. Something very simple. Okay, so let's say this line has equation y. I don't know why it kind of gets locked up sometimes. Y equals x. And I'm going to draw an orthogonal line to that line. That means that those two lines are at right angles. What's the equation of the blue line? What's the equation of the blue line? Y equals negative x. That's right. So we have here y equals x, which is, 1 times x. That's the one line. And the other line is y equals -1 times x. Now you have two perpendicular lines. Here's the slope of the first line. The slope of the first line is 1. The slope of the second line is -1. Okay, what's true about two lines that are perpendicular? What's true about their slopes? Do you remember the rule in from Calculus 1? If you have two lines, L1 and L2, that are perpendicular to each other, what's true about the slope of the first line? Opposite and reciprocal and negative. Good. So how many recall this? That if you have two perpendicular lines, their slope, the slope of the first line is equal to -1 over the slope of the second line. How many recall that from Calculus 1? Okay, Jacob remembers that, and let's see, Leping and Sean, and yeah, that's something you should have learned in Calculus 1, or you should have learned it earlier. But hey, but you can see that it's verified here because 1. The slope of that line there is equal to -1 divided by, hold on, let me do this a little better here. Hold on. For this little example, and a lot of times I have examples that I like to kind of help me feel comfortable with concepts. I think of a little example, and here's a nice little example. The slope of the first line was equal to 1. That is equal to -1 over the slope of the second line, which is -1. Right? It checks out for this little example, and it kind of motivates the definition. So now we're gonna make use of this. We're gonna make use of this. Let's go back to the book and continue that example we were looking at. So the family of parabolas, their derivatives are dy dx equals y over 2x. Well, this means then that the orthogonal trajectories to that family, which would be perpendicular, the intersection points would be perpendicular. That means their slopes, the slopes of the orthogonal family of trajectories, would have to be the negative reciprocal, which is dy dx equals -2x over y. All right, is that okay? Are there any questions on that? All right, well then that being said then, what is the family of solutions that follows this differential equation? What does that family look like? Well, the family, if what we're going to do is separate the variables, and if we do that, we'll get the integral of y dy equals the integral of 2x dx, and we end up getting x squared plus y squared over 2 equals a constant. That's the family. And what would that family be, by the way? That in the highlighted box there at the bottom, x squared plus y squared over 2 equals a constant. The constant of integration, when you integrate both sides, you're going to get a constant of integration, right? You'll get constants of integration on both sides when you separate the variables. But you could just then say, well, all right, let me just combine the constants and put the constant on the right, like they've done here. What's that a family of? I mean, let me put it another way. you have x squared plus y squared over 2 equals a constant. Now, if you don't mind, I'll put a 1 over the x squared, underneath the x squared. This is a family of what? What do those curves look like? You know, if you have an x squared over 1 plus y squared over 2 equals 4. X squared over 1 plus y squared over 2 equals 9. Nathan, you're almost right. If it were a circle, you'd have to have a 2 underneath the x squared.
An ellipse.
And then that's right, Samuel. So you were close, Nathan, but that's right, Samuel. It's an ellipse. It's an ellipse. Very good. So what we have here, are a family of ellipses. Okay, we have a family of ellipses. So the orthogonal trajectories are a family of ellipses, okay, given by equation 4 and sketched in figure 9. And this is again why, you know, we could solve this explicitly for y, but sometimes you don't want to. Okay, sometimes you don't want to, like in this case. So here in figure 9, you have the family of those sideways parabolas, and superimposed with them is the family of ellipses. And the ellipses are wider in the y direction than in the x direction, and that makes sense because in the underneath the x squared you have only a 1. You know, that equation, x squared over 1 plus y squared over 2 equals a constant. Since the number's bigger under the y squared variable, you know that the vertical axis, the y-intercepts, are going to be further apart, making it thinner and making it longer in the y direction. Okay, how many think this is pretty cool, pretty fascinating? Okay, Jacob's liking it, and Tao likes it. Yeah, it really is pretty cool. It is pretty cool. All right. I want to do one more example with you. I'm going to stop the recording on this, and then I'm going to go to the next example. I want to do a new recording for the next example.